Alright, good afternoon. This is Miss Lynham, and we're going to do a little recording on some biochemistry. This is chapters 2 and 3 in your Hillis book. We're going to see if we can knock out some of this basic biochem right now. So, here we go. Rock and roll. First thing, elements. There are 92 naturally occurring elements that occur to nature and how they're important to living things. Remember, elements are things that cannot be broken down without losing characteristic properties. So they're basically in the smallest form that they can be in without losing properties and becoming something else. Examples that you might know: carbon, oxygen, gold. The ones that are important to us for biochem are what I call the sponch elements, S-P-O-N-C-H. These 6 elements comprise 99% of all living matter, because the C-H-O-N, carbon, hydrogen, oxygen, and nitrogen, comprise 96% of all living matter, and then sulfur and phosphorus make up 3%. So between those, 99% of all living matter is made up of these 6 elements. So you might be asking, what is the remaining 1%, because there's 1% left over. These are called trace elements. Trace elements are things that are needed in minute amounts, but don't think that just because they're needed in minute amounts that they're not important, because you probably have heard of iron, which is one very important trace element that is needed for proper functioning of hemoglobin. Hemoglobin is an iron-containing protein that's found in the middle of a red blood cell, and you must have adequate iron supply in order for hemoglobin to do its job, which is to bind to oxygen. So iron is a very important trace element that if you don't have enough of it, you might have a condition known as anemia. You might have also heard of iodine. Iodine is really important for the functioning of thyroid glands. We also need other trace elements like zinc, copper, etc. So these trace elements, even though they're in the 1% category, they are very important to human life, and not just human life, but life altogether. Okay, but especially for us in the human body, these 99%, these elements, these 6 elements make up 99% of our body, which is pretty important because that's you and me. Okay, a couple little basic pieces of information that you probably remember from chemistry, because you're all geniuses, and that is the atomic number. Let's not forget that that number is the number that identifies the element. That atomic number does not change. Okay, does not change. If it changes, then it becomes a different element. Okay, so like hydrogen on the periodic table is number 1. It has always been number 1. If we change that atomic number, it's no longer hydrogen anymore. If it changes and it's number 6, it's not hydrogen. Now it's a different element, so it's going to be carbon. So that's kind of the important thing about the atomic number. Now it is also equal to the number of protons, and in most cases, it is equal to the number of electrons. The reason I say most cases is because if it is in ionic form, then it might have lost an electron or gained an electron if it's involved in an ionic bond. So that's most cases with the number of electrons. Okay, example, this is how we would write, there's several ways you could write this or see it written. This could be as a subscript written to the left. Okay, that's carbon 6. You would get from that information that it has 6 protons and 6 electrons if it's not in an ionic form. And based on that, you could also look then at the next thing, which is the atomic mass, and try to figure out other things like maybe the number of neutrons. Okay, so this is another way you might see it written, okay, like this. You've probably seen this in chemistry before. So the number at the bottom, the 12, this is the atomic mass, and this one is the atomic number at the top. Okay, so using the information, if you look down here, the atomic mass is equal to P's plus N's, protons plus neutrons. So if I know it has 6 protons, and I know the mass is equal to P's plus N, I can use a little bit of math and take 12 minus 6, because 12 is the atomic mass, minus my number of protons, and I would know that it has 6 neutrons. Okay, so that's just a little bit of basic chemistry info. Okay, right in this next section, you will see protons, neutrons, electrons. Okay, let's not forget their location. Inside the nucleus, this is where we're going to find positively charged protons, and then we'll find neutral neutrons. These little red ones are the neutrons that are neutral. So in the case of carbon that you see here, carbon has 6 protons, 6 neutrons that make up the center, which is the nucleus, which, by the way, has an overall positive charge because those protons outweigh the neutral neutrons. And then our electrons, which are negatively charged, are found out in the orbitals orbiting around. Okay, just to show you really quickly, this is the Bohr Model. If you remember from chemistry, the Bohr Model, whenever you plot your electrons, the first orbital can have 2. If my pen will work. The first orbital can have a max of 2 electrons. The next orbital can have a maximum of 8. So because carbon, if you go back up here, has 6 electrons, I'm plotting 2 in the first orbital. That leaves 4 left over. So 1, 2, 3, 4, and they're spread equidistant from one another. Okay, so that's a little bit about that. Okay, the next concept is the word isotope. Okay, not to be confused with isomers that we will talk about in a couple of minutes. But an isotope is when an atom has a different atomic mass due to a change in the number of neutrons. This can happen in the case of carbon. This is quite, it's not common, but it can be found whenever carbon decays, the nucleus decays, the number of neutrons can be different, and then you would have, in this case, C14. So instead of being C12, C12 is what it normally is, that's the atomic mass, it can exist as C13 or C14. C14 happens to be very radioactive. They've used this in science for a couple of things. You might have heard in testing for people with cancer, you might have heard of a PET scan, where you can give someone a PET scan, which is kind of like an MRI or CAT scan. You can inject them with a radioactive material, this radioactive isotope, and it can light up whenever the person takes a PET scan, so it can be used in cancer detection. It can also be used to detect kidney disorders, because you can also inject the person with a radioactive isotope and it adheres to the kidney cells. So this is kind of important in life, in biology, because of that isotope form. Okay, next slide, talking a little bit about chemical bonds. Oh yes, I remember this in chemistry. Bonding, okay, a bond is formed whenever we have 2 or more elements that are combined in a fixed ratio. We have to have 2 or more elements. Okay, these are called compounds whenever we have these. So the bonding might be, let's say, an ionic bond, it might be a covalent bond, but the resulting substance is going to be known as a compound. Where I'm going to also introduce the word molecule with you in a minute, but it's when we have 2 or more elements that come together in a fixed ratio. Okay, in order to determine the type of bond and to see what is going to happen, I'm going to put a star here. We're going to be looking at those valence electrons. Hopefully you remember those are the ones in the outer shell, the outer electrons. So depending on how many valence electrons it has in that valence shell or in that outer shell, that's going to determine the chemical behavior of an atom. That means, is it going to be more likely to want to receive electrons? Is it going to want to give away electrons? Or is it going to want to share its outer electrons in order to reach a stable state? Okay, so atoms interact with each other to complete their valence shells because that's the natural tendency. They're going to either transfer, that's in the case of an ionic, I can't spell with this little pen and I'm having a little trouble with my movie, but that's in the case of an ionic bond, or, I can't even write it, here we go, ionic bond for transfer, or it could be a covalent bond if it's the sharing. The sharing is going to be our covalent bond that we're going to look at. So when you look at the elements that you see in the picture down below, you can kind of see, for example, here's oxygen. It only needs 2 more electrons to fill its valence shell, so it's probably, most likely, it is going to be involved in covalent bonding, and you can assume that the things that are in the same row, or the column, excuse me, on the periodic table are going to also react the same way. So sulfur, still needing 2, is going to react in a similar fashion to oxygen, and so you can use the same properties that you learned in chemistry. Okay, so let's talk about the type of bonds rather quickly. I don't want to go into a lot of detail because this is chemistry information. But if you look in the screenshot here, the first bond is ionic. Okay, so whenever we have an ionic bond, we're going to have the resulting substance, we're going to get ions. That's why the bond is an ionic bond. So we're going to get charged particles. Okay, a more appropriate name for these, cations and anions. A cation is a positively charged ion. The anion is the negatively charged ion. Okay, the negative ion and the positive ion. I always remember that because this T in cat looks like a plus sign. So the cation is the positive ion. So in the picture below that you see here, this is sodium and chlorine. When they react with each other, if you look at their valence shell, sodium has a valence of 1. It has 1 valence electron. Chlorine has a valence of 7. So chlorine would need 1 more electron. So this electron would be transferred from sodium to chlorine. Well, if it donated its negatively charged electron, that's going to make sodium result in a positive charge. Well, as you can see over here, that's the positively charged resulting substance. This one's going to gain that negative electron. This one's going to have an overall negative charge. So you can see in this completed picture, this valence shell is filled on the outside. This valence shell is filled because sodium gave away its electron, chlorine received it. The bond that's between them is the ionic bond. They're both happy now, but we have a positively charged ion and a negatively charged ion as a resulting substance. So my sodium, this is my cat ion, this is my an ion as a result. Okay, so the resulting substance, just so you know, this word electronegativity, one atom is going to want to pull that electron from the other one, so the electron is stripped away. So in this case, chlorine is more electronegative than sodium, so that electron is stripped away from sodium due to chlorine's electronegativity. Okay, does that make sense? All right, next slide, the covalent bonds, which, if I can get this to work, there we go. The covalent bond is much different because this one we're going to have sharing of electrons. This is a more stable bond. Both bond types are strong, but this one is more stable. It's not going to be called a compound necessarily. There's a special name that we can give to things that are formed through covalent bonding. We refer to them as molecules, okay? So we can have examples of ones that share one single pair of electrons. That's a single covalent bond. Sometimes there might be two pair of electrons being shared, which is a double covalent bond. So like in the case of oxygen that you see right over here, an oxygen and another oxygen, both of them needing two valence electrons, they can share this oxygen right here, let's say that's its electron, and this is the other electron. It's going to share that with this oxygen and that one, and then the same thing with those two. So this would be a double covalent bond between two oxygens, also known as O2. Okay, so this is a much more stable substance, and we're going to refer to it as a molecule. So that is an oxygen molecule. Okay, now some of these can be, this is where we get a little more particular, some covalent bonds are nonpolar, some are polar. This is going to be particularly important when we're talking about life, because in life, we're going to definitely refer to water, and water is a polar substance. So other things that are polar, like water, so we're going to be referring to these, but water definitely has polar covalent bonding involved in it, and I'm going to show you why in just a second. So as far as like relating to biology is the study of life. This bond type is going to be more common and more important to the human body because our biomolecules are going to have covalent bonding, okay, that are part of them. Okay, so let's look at the difference between a non-polar covalent bond and a polar covalent bond. I think it's really easy to see the difference when you read right here about the polar covalent bond. It's when one atom is more electronegative, okay, so it's going to have a tendency to be more electronegative because of an unequal sharing of electrons. So that gives a charge at one end that is different from the other end. Oxygen is the most electronegative element that is out there. We're going to definitely want to know that because when we get to talking about cell respiration and photosynthesis, oxygen is going to be something that we go back to, and I'm going to say, guys, remember what element is most electronegative? So oxygen is the most electronegative. So if you look at water, if I can show you right in here, whenever you have water, okay, we obviously know there's two hydrogens and we have one oxygen. That's the formula for water. Well, hydrogen on the periodic table has one electron. I'm going to call it colored in black. So here's another hydrogen, the second one in the formula, that it has its one electron. Well, oxygen having 6 valence electrons needs 2 more to be stable. So I'll change the color and I will use a green here. Okay, so let's see if I can get my pen to work. Okay, right here and right here are the 2 that are in question. Okay, so the other ones are out here, 1, 2, 3, 4, there's 5 and 6. So if oxygen and this hydrogen come together, they can share this one, and now hydrogen's satisfied. Oxygen can share this one, and now that's satisfied. Same thing here. So we end up getting a molecule as a result of this. This is our molecule. Okay, but what I wanted to show you is, remember the nucleus is positively charged, positively charged, positively charged. But the oxygen nucleus, okay, this pen is driving me crazy. Hang on, let me erase this so I can show you really quickly. Okay, the oxygen nucleus is positively charged, as well as the hydrogen nucleuses being positively charged, but oxygen has 8 protons. That's a lot more positively charged, so these electrons are going to have a tendency to pull in toward that oxygen nucleus. They're going to be drawn in. Well, that means that they're hovering around the oxygen molecule. Okay, as they hover around because they're drawn to that positive nucleus, that still leaves, that's a negative, that's a negative, that's a negative charge, that's a negative charge because those are outer electrons. The problem with hydrogen is it has 1 electron and it's involved in that covalent bond, plus it's being drawn into that positively charged oxygen nucleus. Okay, so over here there are no electrons orbiting on this side. So that leaves this side a slight positive because all that you have is this positively charged nucleus. Okay, so this side is slightly positive. So with water, we end up in polarity because of an unequal sharing of those electrons whenever you look at the overall molecule. And that is exactly what this picture is showing you. Okay, so let's just kind of reiterate that so you can have this for your notes. Water is an amazing substance. It is polar. Polar means one side positive, one side negative, due to that unequal sharing of electrons. So go ahead on your drawing, and if you will, let's go ahead and put positive, okay, over here, positive. This is negative and negative. The reason I drew 4 is because where this pair of electrons is, that gives that a partial negative. Where these electrons are, that gives this side a partial negative. Where this positive nucleus gives this side a partial positive, and same with this. That's important to know because each water molecule could actually bond to 4 other water molecules because of its polarity. Okay, so being a polar substance is because of that unequal sharing of electrons. Okay, make sure you know why. Like, why is it polar? Okay, the hydrogen bond aspect, a hydrogen bond is not a true bond. Okay, not a true bond. It's not like covalent and ionic bonds where we're going to have sharing or we're going to have transferring of electrons. This is an attraction, okay, attraction between things that are oppositely charged, okay, and obviously the things I'm talking about is you've got hydrogen, which is a positive charge, being attracted to something else that has slight electronegativity, okay, so that's why it's called a hydrogen bond. It's an attraction between a positively charged hydrogen and something else that is slightly electronegative, which means slightly negatively charged. Not a true bond because this has absolutely nothing to do with valence electrons, guys. Nothing to do with valence electrons. This has to do with the electronegativity and the attraction. So if you look at this picture right here, okay, if you know that this hydrogen side has positive, positive, and you know that this side is negative, negative, if I have a second water molecule come up, the positive part of this water molecule attracts to the negative part of that one. So right in here, I would have, let's see, let me change colors. Right in here, I would have a hydrogen bond, and it's usually represented by 3 dotted lines, 1, 2, 3. So I would have a hydrogen bond there, and I would have a hydrogen bond there. Okay, which is a weak attraction, a slight attraction between 2 polar molecules, and in this case, the positively charged hydrogen, and something else that is electronegative, which in this case is oxygen. Okay? Okay, now, those 2 things that you just heard me say, polarity, right here, the polar nature of water, as well as its ability to form hydrogen bonds, are going to give it some very amazing, awesome properties, okay? So on this screenshot, if I could get this to work, okay, on this screenshot, these are properties of water. These properties are a result of H bonding, okay, and its polar nature. Those 2 things about water allow it to do what you see here. Okay, so look at the first bullet, says stickiness. Water being sticky. You've actually seen this before because sometimes water sticks to your body. It'll stick to your skin. Water might stick to a spider web. Water might stick to itself. So you see the little arrows. We have a couple little bullets here that we're going to talk about in regards to the stickiness of water. Okay, the first word is cohesion. Co, you know this is one of your words, means together. Okay, together. Hesion means to stick. So this is to stick together. This is water sticking to itself. Water to water. Water sticking to itself. Okay? Water sticking to itself, look down here in the picture, you can kind of see it. If I have this, let me pull the screen down. If I have this water molecule right here, it can stick to another one and another one, so water sticks to water, cohesion, due to the fact of hydrogen bonding. I'm drawing it right here. Okay, my attraction between my positively charged hydrogen and my slightly negative oxygen, that hydrogen bond that forms allows water to stick to water. That's water to water. That's called cohesion. It's sticking to itself. What does that do? How is that beneficial? It gives water, it gives water surface tension. This is the picture of what surface tension looks like. You can see the spider down here. Surface tension is how difficult it is to stretch or break the surface of water. Water has an amazing strong surface because of the fact that it can hydrogen bond with itself. Now you couldn't do this, you couldn't walk on water because we weigh too much. But light things like spiders and water gliders and striders and things that walk across water, they can do that because of the fact that water itself has a great surface tension due to it sticking to itself. Okay? Now there's a second thing that you actually see in this picture as well, and it's where the spider's leg right here sticks to the water. There and there and there. That's because of the second property of water called adhesion. Okay? Ad means unlike. Okay? Unlike, if you remember your root words. Unlike. Okay, so this is water sticking to an unlike substance. This would be water to glass. Okay, I'm going to just kind of bring it down here because I can't do it over there. Water to glass, water to plastic, water to skin, water to the spider leg. So adhesion means water sticking to an unlike substance. Okay, it might be water to a tree. Okay, water to a pipette. So cohesion and adhesion are stickiness, are actually referring to the stickiness of water because it can stick to itself and it can stick to other things, and those other things that it's sticking to are also polar. Okay, capillary action is something that we'll talk about. You've probably seen that if you've ever had your blood taken before. Capillary action is if I took a pipette or even a straw, let's say. Okay, if I took a little straw and I put it into a cup of water like this, so here's my cup, and here's water inside of it, the water would rise on the inside of the straw. Even without you sucking on the straw, water would naturally come up, and that's called capillary action because it is adhering to the inside of the straw, and it's also sticking to itself. So capillary action is the rising of water on the inside of, let's say, a pipette, a straw, or something that's glass, or it might even also be on the inside of a plant, being able to come up through that. So in this picture you can see this is definitely important to you, even though you're not a tree, but we depend on plants. They're our producers. But you can see in the picture, cohesion and adhesion contribute to the transport of water and nutrients to be able to go against the force of gravity, to be pulled up in plants. So water movement goes from roots up to the shoots, up to the leaves of the plant, due to the property of water, it being able to stick to itself and stick to the inside of the plant to rise. And you can see in this picture is a great description. If this was the trunk of the tree or the inside of the tree, like right here, you can see water to water is this to this to this, and then water to the plant is adhesion there, or right here. So we've got cohesion and adhesion both going on in that picture. Okay, makes sense? All right, let's see really quickly. We're going to take a little pause. Okay, so the next part about water, as you can see on this slide, is talking about regulation of temperature. Okay, so water is very important because of temperature regulation. There are two properties that you see listed right here by the arrows. One says high specific heat, and one is high heat of vaporization. Okay, both of these properties, and actually the third bullet down here, which is water is less dense as a solid than it is as a liquid, all of those are a result of what you can see right here in the picture, which is hydrogen bonding. So the fact that water molecules can hydrogen bond to each other gives it the great immense high specific heat that it has, as well as high heat of vaporization. So let's talk just really quickly about high specific heat, the first one that you see listed here. Specific heat is defined as the amount of heat that must be absorbed or lost for 1 gram of that substance to change its temperature by 1 degree Celsius. So water has a very high specific heat. Because of that, water will change its temperature less when it absorbs or loses a given amount of heat. Okay, how is this important to life? Think about, let's say, a big, Lake Houston, or a big large body of water like a lake or a pond. It can absorb and store a huge amount of heat from the sun in the daytime and during the summer while only warming up a few degrees down below. Okay, also at night and during the wintertime, the gradual cooling water can actually warm the air, which is the reason why coastal areas generally have milder climates than inland regions. So it kind of helps to stabilize ocean temperatures, which creates a favorable environment for marine life. So it kind of helps to not have temperatures fluctuate so much. Okay, so the second one that you see is high heat of vaporization. It's basically the quantity of heat that a liquid must absorb for 1 gram of it to be converted from a liquid to a gaseous state. As you can see in the picture here with the person that's sweating, for us it helps to cool our bodies off. Whenever the sweat is like in liquid form on the face and on your body, on your head, etc., when it evaporates and changes into that gaseous state and lifts off your skin, the evaporation of it cools our temperature. So for temperature regulation for us and being outside, and especially us living in Texas, it's definitely a very important property for us. Okay, the bullet right here where it talks about water being less dense, density of solid water is less than the density of liquid water. This is so cool. You've probably tried this before. I'm sure that you've all frozen a water bottle, put it in the freezer, and you probably filled it too full. You got it out the next day, and water was like coming out of the water bottle. And this is because of this property. So in the picture, what you see here, it's kind of cool. This is showing you ice. Okay, so imagine these little blue water molecules with the little yellow hydrogens. If this was liquid, these would all be really close to each other, just kind of bobbing next to each other, and their hydrogen bonds would be really close. But the cool thing about water is right as it's about to freeze, it gets close to that freezing point, these hydrogen bonds, they lengthen, okay, so they get really long, and they push each water molecule, what we call is they're at arm's length to each other, which means they push the water molecules pretty far away, which creates this lattice-like appearance. Okay, it's called a crystalline lattice, and due to the lengthening of these hydrogen bonds. But if you were to melt that ice, those hydrogen bonds, as the water's melting, they get shorter, and so the water molecules get closer together. So the expansion of it is kind of what we see. If we freeze water, you'll see it expand, which is a cool thing. Now, as far as like how does this help life, if you think about down here at the bottom, if ice sank, then all ponds and lakes would be frozen at the bottom, and then that would have an impact on the fish and all the marine life and the pond life and everything that was inside of that body of water. So it's important that the ice stay at the surface so that the water down below can still have the living things that are all swimming around. Okay, the next property of water is kind of the bullet right here. Water is a powerful, or I like to call it versatile. Water is a versatile solvent. Okay, a little bit of chemistry review. If you remember, solvent is the water. Okay, let me see if I can use my pen. I had to plug my Moby in because it's giving me a little trouble. But the solvent would be the H2O. What you put in the solvent is called the solute. And in the case in this picture, that's salt, NaCl. And so what we get as a mixture is the solution. Okay, so the solution is the solute mixed in the solvent to get our homogeneous solution. So anything that we put in water that is dissolvable, or I like to say soluble, we would use the term hydrophilic. Use your root words, guys. Hydro is water. Philic means loving. So anything that is water-loving, we call it hydrophilic. Polar molecules are hydrophilic, because if we take a polar molecule, such as NaCl, I'll go back up here and show you. Remember, ionic bonding, The Na is positively charged, the Cl is negatively charged. That's a polar molecule. If you put that into water, with water being polar, you can see in the picture here, the water molecules, right here, can you see this one right here? They put themselves around the salt so that the hydrogen part of the water molecule, the blue part, is facing the negative ion, and in this case the chlorine is the negative ion. So if you look, you've got the blue dot here and the blue dot here because those are positive and they're sticking to the negative chlorine. Same thing over there, there, and then here and there. So the part of water that is positively charged sticks to the negative particles and vice versa to the positive positive Na, then the other part, the negative part of water, will stick to that as well. So anything that's hydrophilic loves water and can be pulled apart. Ionic compounds are those that are better to be pulled apart due to their polarity. Okay, if it's hydrophobic, use your root words. Phobic means fearing or hating. Okay, so we call these water-hating or water-fearing things. This would be like your oils, fats, and lipid-type substances that are definitely non-ionically bonded, they're non-polar, and therefore they're or insoluble and hydrophobic, repelled by water. Okay, make sense? All right, next couple of slides, and then we'll be finished with water. We want to talk about the dissociation of it. This is kind of a cool little property. You probably studied this in chemistry as pH. That's when most chem kids will get this. But water can occasionally, it is rare, but occasionally it's a measurable phenomenon that it can dissociate. Okay, dissociate means to split apart. Okay, so water can be pulled apart. If you look down in this diagram, it shows you that here's one water molecule, there's an H2O, here's another one, H2O, and there is our hydrogen bond, okay, right there between them. Occasionally, this is a rare phenomenon, but it can be measured, and it's very important to life, is you can have, let's say, this hydrogen be pulled apart from this water molecule and go over to this water molecule, and it now, because there's an extra H added on, it's now called a hydronium ion. It's H3O+. So this is what it would look like. So this is a positive ion, a hydronium ion. What's left behind is the OH, which becomes negative. Okay, if you want to know why the positive is because H, hydrogen, has a proton. It's a positive ion. So the H comes over here, makes this a positive ion. This OH becomes an OH negative ion. We call that a hydroxide ion. So if water dissociates, you get this hydronium ion and a hydroxide ion as a result of that. Okay, how is this important? Because this can happen when you put things in water, and we know this as being acids and bases. Okay, so we can take something, put it in water, and water can dissociate, and we get a resulting substances called acids and bases. So I want to show you, and there is actually a mistake right here, so I need y'all to fix this on your notes. This should not be a plus sign right here. This is product, okay? So in an aqueous solution at 25 degrees Celsius, the total concentration of hydrogen ions and hydroxide ions, the total concentration, is equal to 1 times 10 to the negative 14th power. Okay, so this is pH. pH, by the way, is a scale. It's a tool. It's a tool/scale that can be used as a means of measuring how acidic or how basic something is. Okay, you probably remember this from chemistry or even my class, but whenever you're talking about acids and bases, it means when you put that substance in water, is there a higher tendency to have H+ ions, or is there a tendency to have more OH negative or those hydroxide ions? But to figure out, because you're always going to have some of each ion, even in a neutral solution, you're going to have an equal number of those, which is what you see down here. If the solution is neutral, such as water, the pH on the scale is a 7, but that's because H+ ions are equal to OH negative ions. Okay, so that's in a neutral solution. But if you know how many H+ there are, you can figure out how many OH negatives there are by using your algebra skills with the exponents, because the product of these two is equal to 1 times 10 to the negative 14th. Okay, so as you increase or decrease, it's by 10 times because it's base 10. Okay, so what we're going to define is, go ahead and get your vocab down first, An acid is any substance that when you dissolve it in water has an increased number of H+ ions, okay, compared to its OH- ions. Okay, so read this right here with me so you can kind of see it. So what we're going to have is, if H+ ions, they're greater on the side that goes below 7. Okay, so the pH is going to be below 7, it's an acid, and the H+ ions are greater than 1 times 10 to the negative 7. So I'll show you the scale in just a second, but an example of a powerful one is hydrochloric acid. Okay, if it's a base, it's going to have decreased numbers of H+ ions. Okay, so the H+ ions are going to be less than the 1 times 10 to the negative 7th, and the pH is going to be greater than a 7. Okay, so this is sodium hydroxide, which is a powerful base. So let me show you on the scale what this is talking about. Okay, this is a better example when you see the scale. Okay, so on the scale, my little dogs are barking at y'all. Hang on. Okay. Alright, so let me show you on the scale what this is talking about. Okay, so here's the neutral solution. So down here at the bottom, this is what you guys remember from chemistry. The scale goes from 0 to 14. So when you're telling somebody, oh, we're using hydrochloric acid, and hydrochloric acid has a pH of 0. Okay, that's just basic information as far as, yeah, the 0, that's the strongest. Okay, down here, this is the strongest acid that you can get, is a pH of 0. Whereas if you went down here to a 6, let's say 6.9, right there, a 6.9 is a weak acid. Okay, we're still on the acidic side, so these are acids on this side, and these are bases. Okay, so let's get just our bearings here. So from 0 to 6.9 is an acid, 0 is the strongest acid, 6.9 is the weakest acid. A 14 is our strongest base. Okay, this is the strongest base. A 7.1 would be a weak base. So as we get closer and closer and closer to 7, whether we're going bases this way or acids this way, we get more neutral. Okay, so the 7 is the neutral number. So these are just numbers in reference to that. But if you look at the change in concentration of ions at the top, this is what I want y'all to understand is at neutral, at 7, right here, the concentration of H+ ions is 1 times 10 to the negative 7. And the concentration of OH- ions is 1 times 10 to the negative 7. So this concentration is equal. So here's the important thing. Let's say I change, and I have a neutral substance, that's right here, and I add an acid to it. Okay, so let me mark it right here. Here's my neutral substance, and I add an acid to it that changes my acid to this right here. So now, if you look up here, I changed my H+, I just increased how many H+ there are. So my H+ are now 1 times 10 to the negative 5. Okay, well that means I also changed how many OH- ions to 1 times 10 to what? Anybody know? Okay, well the product of these two must be 14, 1 times 10 to the negative 14th. So this has to be 14, do a little bit of your algebra. So 13, 12, 11, 10, 9. So this is going to change to the concentration of hydroxide ions will be 1 times 10 to the negative 9, whereas hydrogen ions 1 times 10 to the negative 5. Okay, so that's what it would change. Now, as far as like how much did it change, what I could say is if I added an acid and I went from here to here, this acid is now, ready? 10 times 10 is 100. Okay, so it is 100 times more acidic than a neutral solution because these are log 10. These are increasing in tens. So if I change from a 7 to a 5, a pH of 5 is 100 times more acidic than a pH of 7, which is at a neutral substance. But I wanted you to see this part up here about how to figure out the concentration of those ions. Okay, make sense? Cool. Cool beans. Okay, the last slide for today's little recording is still dealing with pH and the human body because, of course, we have to apply that to you and me and all life. But this one is really important to the human body in particular, and it's maintaining what we call a buffer system. Okay, our bodies are able to maintain a constant pH. Okay, if you remember correctly, this is maintaining homeostasis. Homeostasis is a constant internal equilibrium. Well, pH is one of those things that must be maintained in a constant internal environment. So the pH of our blood is 7.4. Okay, so if you think about the scale we just looked at, it's relatively neutral, okay, a little bit above neutral, but we have to maintain that constant pH. So your body has a buffer system in place. It's called a bicarbonate buffer system that is really cool because it can donate or accept hydrogen ions to keep our blood pH at a 7.4. Okay, so if you look down here at the little equation, you can see the arrows go in both directions. That means this equation is reversible, and it's constantly going in both directions depending on what the blood needs to do to maintain a 7.4. So carbonic acid, which is H2CO3, can be formed when carbon dioxide reacts with water and blood plasma. Okay, so let's look at how this equation works down here. If the pH rises, okay, pH rises means goes to like 8, 9, 10, okay, so ready, 8, 9, 10, etc. If the pH rises, hopefully it doesn't get that high because you're going to be like in some serious trouble, but let's say it rises to 7.5, 7.6, 7.7, the reaction will proceed to the right. This arrow will occur because if it's going up to 7.5, 7.6, 7.7, that means it's becoming more basic, okay, and if it's more basic, we need to get it back down, so we need to have more hydrogen ions in the blood. So your body would go take this carbonic acid, start splitting it up, and if you notice it split up, you'll get HCO3 negative, and then you'll get some hydrogen ions. Well, if you increase these, you're making it more acidic, which is what we're trying to do. If it goes up to an 8 or 9, we got to bring it back down. Not that it's becoming acidic, we got to bring it back down to a neutral range. So we have to lower those OH negative ions and get more H plus ions. Okay, if the pH drops, okay, so if, in other words, if we go down to a 7 or a 6 or something like that, that means we're now on the acidic side, hydrogen ion concentration went up, we have to make this reaction proceed to the left. We have to remove these H pluses from the blood and cause them to be stuck with this to create that. So we're constantly taking H plus ions and releasing them when we need to get the pH back to 7.4 and taking them up when we need to get it back to 7.4, depending on if it's above that or below that. Okay, that will conclude this lecture. The next one will be on basic organic chemistry. Hope you enjoyed it.